Welcome back. So now we are looking at the implementation of this thing. How do we implement a data warehouse? How do you implement data cubes? In particular, how do you implement the slicing and dicing of, of data cubes? Let me first start with general considerations on what to do when you have to implement a new system, a new shape, a new model, a new query language, and so on. If you're very ambitious, you can think, okay, let's re-implement something from scratch, just like re-implementing a new PostgreSQL, but instead of being for tables, it's going to be for cubes. You could do that. That's going to be very tough, very expensive, and it's going to take you a lot of time, maybe a lot of people too. What instead many people do or try to do first when they want to implement a new model, a new shape, a new language, is that they try to do it on an existing system. Meaning that you take, for example, a relational database that supports tables, and on top of that relational database, you implement your cube database system, right? But the data is going to be stored in a relational database. You hide it from the user, but it's stored in tables, but the user sees cubes. In fact, doing that is a very good idea because typically it's going to be much easier to work on top of a relational database than to work directly at the level of the hard drive. Relational databases, there's plenty of free relational databases. It's very easy to start with. This is a typical way to do it. So what many people do is that they start with the implementation on top of an existing system in a different shape. And then later, maybe they end up doing the whole system completely from scratch. But this is something they do later when they have gathered experience. In the case of cubes, the people who had the excellent idea of trying to implement support for cubes on top of tables, this is called rollup. So OLAP is probably easy to understand. Why? R is for relational OLAP. There is another one that's called MOLAP that is that would be the native one, right? So rollup is implemented on top of a relational database management system, and MOLAP is a native implementation of OLAP Cube. There is another one that's called HOLAP that is for hybrids, that is kind of in between rollup and MOLAP. For the purpose of this lecture, I'm going to show you rollup, the one on a relational database management system. Why am I doing that? Well, because we spent weeks on relational database management systems. You know tables, you know SQL and so on. So you actually have everything to understand how this is going to be done. On top of that, it's going to be normally relatively simple to understand, simple enough that I can just do it today, right? Of course, it's not going to cover everything, but it should give you an idea. MOLAP would be more involved because MOLAP is not implemented on top of a relational database. It's really directly on top of memory and disk, right? So this would be much tougher to understand. Now, probably you understand why IBM, Microsoft, and Oracle purchased these cube data analytics companies. It is because they have the relational database management system. There is the IBM one, the Oracle one, and the Microsoft one, right? So they all have a relational database management system. And when they purchased the data cube companies, all they needed to do is add it on top of their relational system. Okay. So the first thing to understand is why do we think, or why would we think of implementing support for data cubes on top of a relational database management system? Well, you probably already kind of guessed the answer, is that look at this facts table. What is a facts table? It is a relational table. So why don't we go ahead, take this facts table and literally put it in a relational table, literally. And in fact, this is exactly what people are doing. They are storing the fact table like that in a relational table. So now coming back to this. This here is a facts table stored in a relational table where you have all of the columns, dimension 1, dimension 2, dimension. So there's 5 dimensions here, plus the last column that is the value. Of course, it's a very specific way of using a relational table, right? But this actually works. Who can tell me in a table like that, what is my primary key? checking your understanding. What is the primary key of a fact table? Does anybody on Zoom know?
I think the union of dimensions.
Yes, exact. All dimensions together, so this here to here, all of these together are the primary key. Remember that a primary key is a list of attributes, it's several attributes. So the primary key is dim1, dim2, dim3, dim4, dim5 together are a primary key. In fact, it's the entire table except one column, right? Because that's the one that is indexed. So you could see a fact table as kind of an index, but not as a hash table or B+3, but kind of an index on the dimensions that maps them to a value, right? In fact, this is an even higher normal form to have things like that. I can't remember if it's the fourth one or something else. It's a normal form that basically says that you have all possible combinations of dimensions. That's basically it. So we are not going to go into details of that, but you can think of it as a super high normal form of a relational table where you have a primary key of all columns but one. Okay, now, just so you know, there is an alternate way that people like to do things in this kind of systems. They like to have not just one column for the value, but several, like this, right? So you still have your 5 dimensions, but you're going to have 3, in that case, 3 different columns. This is called a measure. It's called a measure. And what would you want to measure? Well, for example, you could measure revenue, you could measure profit, you could measure cash flow, and so on, but on the same dimensions, right? So you could have as dimensions the country, the subdivision of the company, and so on and so on. And for every combination of dimensions, you have the revenue, the profit, and so on and so on. You can think of it as separate cubes. It's as if you had a big cube for the revenues, then you have another big cube for the profits, and so on, right? So this is what the measures are. But in fact, they are equivalent. It doesn't really matter how you do it, because here is the very simple way that you can go from one to another. Imagine you have that on the right with 2 measures. And to keep things simple, I only have one dimension, who. So I have a measure of revenue and a measure profit. How can you turn that in a different fact table with only one single value? Well, just promote the notion of measure to an extra dimension. Now, if you say we have an extra dimension measure that can be revenue or profit, then I can have just a single value. I just double the number of rows, right? It's a very natural thing to do. This is called pivoting and unpivoting. Pivoting means that you take the column measure, or whatever column you want, but in that case, the column measure, and you turn these values here into headers, column headers. So revenue, profit, you remove them from here, it becomes a column header here, and then you redistribute the values. Here you have these 8 values. Instead of being flat, now you have a 4 times 2 rectangle. It's only a matter of how you organize these 8 values, either as a rectangle or as a flat list, right? Pivoting, unpivoting. For whom is that natural? All right. This is the reason why, for the purpose of my course, I just look at this case where we have only one single column. It's much easier to understand, just because we know it's equivalent, right? You can always come back to doing that. Again, these are called measures, revenue, profit, and so on. Okay. Now, I want to introduce you to what's called the star schema. What is the star schema? It's the idea that you have this fact table, of course, where you have all of your little cells in your big cube, with all your dimensions and the value column. But typically what's going to happen is that what is stored in the dimension columns, these are actually foreign keys pointing to dimension tables, right? So every one of these columns, 1, 2, 3, and so on, they're all pointing to a separate table. They are called satellite tables for obvious intuitive reasons. And basically, these additional tables contain more metadata about the dimensions. For example, you could have a dimension that is CT, and then in the CT dimension table, you have for every CT the canton, the country, the continents, and so on and so on. That would be additional information. Or you could have a dimension that is a date, And then in the satellite table, you have the month, the quarter, the year, and so on, right? Or you could have a dimension that is the ID of a customer. And then in the customer table, you have the name, the address, the phone number, the mailing address, and so on of the customer, and so on and so on. If you have a product, then you have a product ID in the fact table. And then in the product table, you have the name of the product, the price, and so on and so on. So this is a star schema. Well, star schema, because it has the structure of a star. What you notice here is that this looks like a normal form thing, right? We normalized things kind of by putting nicely these dimension metadata separately in other tables, right? And some people like normal forms so much that they even want to normalize the satellite tables, and then you end up with a snowflake schema, which is a very good name for today, given the snow outside. So this is the snowflake schema where you normalize all you can, basically, and then you end up with that kind of structure. What's important is that the fact table is in the middle, and then around that, you just have the dimension data. For whom is that clear? Okay. So here's an example where I have my fact table on the left with two dimensions, one that is the city and the other that I don't care the name of. So city, then you have a satellite table on the first level that maps a city to a country, and then a second level, because I normalized even the satellite table, then I map the country to a continent, right? This is for one dimension that it looks like that. Now, you can, instead of normalizing everything, you can denormalize everything, right? And some people like to denormalize their fact table. What does that mean? You join the fact table with all the satellite tables, and then you get a gigantic fact table, but now you have multiple columns for every dimension, right? Because you just merge everything into the facts table. This is the opposite course of completely denormalizing the facts table. So above, you see the normalized form with the fact table. Let me show you. So above, you have the normal form with the fact table right here. And here you have two meta tables for dimension 1 at 2 levels. And here you have the satellite table for dimension 2. If you merge all of that together, these 4 tables, then you get this denormalized fact table. It's going to be in the first normal form, but it's not going to be in the third normal form. Okay. This is an example. If I take my example here of normalized version, so this is my snowflake schema, and I denormalize it, and this is what I get. This is now my facts table, but instead of having a single column for the where, I now have 3 columns, right? I have the city, the country, and the continent. And of course, you see the functional dependencies there, right? There is a functional dependency from city to country to continent, right? Because if I have the same country, Switzerland, it's always going to be Europe. So I have a functional dependency from country to continent. You see how a beautiful opportunity this is, the data cubes, to actually rehearse on everything we've learned during this semester, right? All of these concepts that we've studied. Okay, so that's a denormalized fact table. So this is the data and the way that I store my cubes as fact tables into a relational database management system. And that can be PostgreSQL, right? I could store this in PostgreSQL. Okay, how do I query that? In terms of query languages, you know already that for tables, you should use SQL, right? There is no real alternative to SQL for tables. It turns out there is a language for cubes. It's called MDX for multidimensional expressions, but I don't want to scare you too much. So I'm just, at the end, I will quickly show you what it looks like, but it's not really part of the material. You should just know that there is one, and that language allows you to slice and dice, you know, and create cross tabulations and so on. What I'm going to do today is I'm just going to go ahead and use SQL as the physical implementation of my data cubes, right? Because we're using PostgreSQL as the physical level for my data cubes, and we are going to do things in SQL today, so there will be nothing new. So I'm going to take an example to show you the sort of things we can do with SQL on fact table to implement the slicing, dicing, rollup, and so on. I'm taking an example of fact table that's a sample cube, where you see that we have 3 dimensions, the date, the product, and the customer, and then we have a quantity, just a single measure. That's the values that there are in my cubes. How many dimensions do I have? 3. On the third dimension, I have 3 values. The second one, I have 2 values, and the third one, I have 2 values. So this is a 3 times 2 times 2 cube. So there are 12 values, right? Who visualizes a cube here? Who sees the cube? You see the cube, right? Okay. So it's a three-dimensional cube, but I'm showing you the facts table representation. Now you have the satellite tables, because as I showed you with the star schema, there is a date satellite table, a product satellite table, and a customer satellite table. Here they are. And now you see that all of the three columns here are foreign keys pointing to primary keys in these three tables, nicely in normal form. You see that for the time, for every date, I have a year and quarter. For the customer, I have a name mapping to a country and a phone number, 555, as in movies, and then products mapping to a brand and price. Okay, so this is the fact table. These are the satellite tables, right? And then you can go ahead. For example, you can query the facts table using SQL like this, select star from sales. You can join with the satellite tables if you want to pull the data together. For example, you want to display the year instead of the date. Then you just select the year, the product, the customer, the quantity from sales and time. So you join the table sales and time, right? So it's this table here with the one on the top, time table. You're joining on the date. And then the joining criterion is S date equals T date. In fact, it's a natural join in that case because it's the same value, right? But I just made the criterion explicit just for the sake of completeness, right? So I'm joining sales and time on the dates being equal, and I'm projecting only the year. So this is why I no longer have the date, but I have the year, okay? This is things that you should already know, right? Who understands this query? Okay, we've already covered that. Okay. But to keep things simple, now I'm going to forget about the satellite tables for a moment. So I'm just going to take a simple case that I projected, or I already did my join, and now I just consider the year, the brand, and the customer, right? So I have my year, my brand, and my customer, and I can forget about the satellite tables. I'm just going to work on that fact table. I'm going to slice, dice, and so on. Okay. This is something I changed this year because I wanted to decouple things a bit and found a simpler way of explaining things. Okay, so how do I slice? Well, it turns out that slicing a cube, given the mapping that I've shown you storing the fact table as a relational table, slicing a cube is in SQL what? What kind of relational algebra operator do I need to do to slice a cube? Yes? A selection. So indeed, remember, we have the logical level, these are my cubes. The physical level, these are my tables. Slicing a cube means selecting on the facts table. Once you understand that, you know that to select, we use a where clause. So all I need to do is where the year is 2017, and there you go, I have a slice of my cube, right? Of course, I'm saying cube, but it's actually the facts table of the cube that we are seeing, right, on the physical level. Okay, so this is how we slice things, right? And then, not surprisingly, we have the slice for the year 2017 with only 4 values left. Okay, I can slice also maybe additionally on the brand, right? So yeah, if I also slice on Samsung, then now I have 1 year and 1 brand only, and then the customer and the quantity. Of course, if I want to do it the same way as before, I could also omit the year and the brand in my projection, right? I could also just have S customer and S quantity. I could have done this too. That would have been fine too. Okay. Okay. Now, but this is easy, right? So slicing a cube is selecting on a table. Now let's try to do fancy things where it becomes really, really interesting. Let's do what's called a roll-up. So a roll-up is the fancy name for aggregation. What does it mean to roll up? It means that we aggregate on the customers and we aggregate on the products, because what I want to give to the CFO of the company is just the yearly data, the aggregated values for the years. The CFO doesn't care about the customer and product. So this is called rolling up. I'm rolling up the customer and product dimensions because now I'm taking all of the customers together and all the products together. What is it in SQL? It's just a group by. All I need to do is group by year, and for every year, I just compute the sum. So this is easy. You know how to do it in SQL. Select the year and the sum of the quantity from the sales facts table, grouping by year, and you see I have every year gives me 1 row in my result, and I have the aggregated quantity. And you can check, because if I did it right, normally, 2017, 1 plus 2, 3 plus 5, 8 plus 3, 11. Do we have 11 here? Yes, we have 11. Okay, so you can do it for all the rest, right? 3 plus 2, 5 plus 6, 11 plus 3, 14. Do we have 14? Yes, we have 14. Okay, so this is the aggregated view. And again, I rolled up the dimensions customer and product all the way up, and I only have the aggregation, right? One number for every year. Now I can roll up even more. What if I also roll up the year? Then I just end up with the total amount, right? This is my entire quantity. I don't even need to group by anything. It's just a sum, right? It's just going to compute the sum of everything. Quantity 34. This is called rolling up, all dimensions. Who is following? It's quite quiet today, actually, but I just want to make sure that just being quiet still means that you're following. Okay. The opposite of rolling up is called drilling down. Drilling down means that you take a dimension that was rolled up and you drill down in it, meaning that you add the details on that dimension. So you might have started here and you want to go in the details. You want to know, okay, what is it per year? What is it per brand? And drilling down basically means that you add back dimensions and you go into details. So here we drill down into year, we drill down into brands, and we add them to the group by. And now I'm going to have the quantity, but more fine grains, not fully aggregated. It's by year and brands. So now I'm back to two columns, the year and the brands, and the quantity, right? So roll up, drill down. Okay. Now, we saw that when you roll up, you need the totals or the subtotals. But in the original table here, there are no subtotals. It's just the raw data on the low level, right? I have for every year and brand and customer, I have my quantities, right? I don't have any subtotals there. But I told you that in the case of a data warehouse, we like to pre-compute things. What if somebody needs the subtotals or totals? We could compute them every time, but maybe we don't want to do that because that's going to be costly. Why don't we pre-compute these subtotals? So in order to do that, we basically need to do roll-ups, right? But several of them if we want to compute all subtotals. So on the left, on the top, so I have 4 queries here. The first query groups by year and by brand. So I'm going to have the quantities for every year and for every brand. The second query is going to give me the quantities for every year. The third query will give me for every brand aggregated. And the last one is the total that goes for every sales. So you could compute the subtotals like this with the union of these 4. Right? So again, if I show you the part of the tables where this all comes from, I had my query right there, grouping by year and brand. This corresponds to this part of the table, right? I have my 3 years, my 2 brands, so 2 times 3 giving me 6 possibilities. This here, the first 6 rows, come from this query. Next, I'm grouping by year and displaying the quantity per year, but I still need a table, a table identical support. So what do I do to fit things? I add a null here in my second column. So you see, these are the 3 rows right here. I have 2017, 2018, 2019. I have a null that basically means it's the total on the brand. So this is aggregated. And here I have 11, 14, 7, right? So you see, this is aggregated 6 plus 5, 11, 9 plus 5, 14, and 5 plus 4, 9, right? So this is for the subtotals on the years. Then I have the subtotals on the brand. So again, I put a null on the left this time to say that it's aggregated over the years. And here I have Apple and Samsung, right? So you see that's 20, 6 plus 9, 15 plus 5, 20, and Samsung 14. So I have 5 plus 5, 10, plus 4, 14. I did it right. And finally, I have my total with null and null, the sum of all quantities, null and null. And this is then 34, right? So you can either see 20 plus 14 is 34, or if you prefer, 11 plus 14 plus 9 also gives you 34. So what I did here is that I pre-computed all of my subtotals and totals and put them in a single table. And you can see that with the nulls here and here and here, I just fit everything together. Okay, so this is a materialization of the subtotals and totals. That's quite a lot to write in SQL, right? But fortunately, the developers of PostgreSQL, they are aware that people do data cube analytics on top of their platform, so they added a few shortcuts. The first shortcut that they add is that you can say group by grouping sets, which is equivalent, and that's equivalent to the union of 4 group bys. The first on year and brand, then the second year on year, the third on brand, and the fourth, the full aggregation, right? Who understands that this is just a shortcut for this? Okay. So this is the grouping set keyword in SQL that is a shortcut for this. So we computer scientists love this because we are lazy and we like to, when we have less to write. So this is a good shortcut. But it turns out there's even a shortcut for this. Because if you think of it, it's a cube, right? There's year and brand, then there's year, there's brand, and so on. You can, in fact, write directly group by cube, year, brand, and this is, again, a shortcut for this, right? So you see how easy it is to create that table on the right. Just say select year, brand, and sum over the quantity, group by cube of year and brand. And by adding cube, without cube, you would only get this, right? But by adding cube, you also compute the subtotals and the total. Right. This is the magic of group by cube. Who understands the group by cube? Okay. Good. But now, of course, the reason we are doing that is that we want a visual. And you probably already know what a visual with 2 subtotals and 1 total looks like. This is pretty much it, right? If we decide to now dice on year and dice on brand, so I'm dicing by putting the year, you know, in Excel, I would drag and drop the year here and drag and drop the brand here. Then I'm dicing the brand here, the year here. And you see for every year and brand, I have my numbers. So you see these 6 numbers right there, these are the ones here. Then I have my 2 subtotals for the brand, these are the 2 here. And I have my 3 subtotals for the year, these are my 3 here. And the grand total 34 is here. So there is a one-to-one. This is the physical implementation in SQL in the relational table. And this is what you need to do maybe in Java, in Python, or whatever language you want to display this fancy view to the final user of these computed values, right? So you see it's on 2 dimensions. I have my subtotals and totals. Now, the user can, of course, drag and drop things and manipulate this dynamically. So for example, we add a slicer on customer Peter. It's hidden behind this thing, but let me move it a bit. Customer Peter. So you see that now the numbers are changing, of course, because this was on all of the customers, right? Aggregated on all customers. Now it's only Peter, right? But I still have my dicer on year and brand. Or I could, on the contrary, slice on the year 2017, and then dice instead on the customer and brand, right? It changes my view again, but this is still the same cube. I'm just, you know, slicing and dicing my cube in all directions, right? Okay. So this is the visual for what we did in SQL right here. So you see it all connects to what we've done before. Now, I want to show you one more thing, which is about rollups, but finer. Because the rollup we did previously, if I show you again the kind of rollup we did here, we just roll up on all the years. We roll up on all the brands, but it's basically all or nothing for every dimension. Either the dimension is here or the dimension is not there, right? So here we have a roll up, so the year is here and customer and product are not here. Here, they are all not here. Here, we have the year and brand and the customer is not there, right? So it's basically just hide and seek. Either the dimension is here or it is not. But in fact, we can also do that on a slightly more fine-grained level. But for this, I need to come back to my satellite tables, in particular to my hierarchies in dimensions. Because in the example so far, it was a flat list of values in a dimension. In practice, in almost all data warehouses and data cube analytics systems, the dimension values are in a hierarchy. The easiest example that we can take for a hierarchy is again with my cities and countries and continents, right? So I have the world, then I have my continents, then I have the countries, then I have the cities, right? Every city is in a country that is in a continent that is in the world. So in practice, I can denormalize my facts table, and we have data, I think, that we can share with you if you want to play with it in a spreadsheet, with 3 columns for the city dimension, We just add also the country and the continents. What does it mean to roll up? Well, instead of rolling up the entire world, I could not directly go to the entire world. Maybe I want to go from the cities to the countries. What it means is I ignore the data for every city, but I still see the data for every country. Or you can roll up a tad bit more and no longer see the data per country, but only per continent. Or you can roll up even more and see the data for the whole world. So you see that roll up is not an all or nothing thing for every dimension. It can also be in finer grains, in a finer grain manner, going down the hierarchy of dimensions or going up. So rolling up means it's literally the image of rolling things up, right? You see this visually, that you aggregate per continent or the whole world, and drilling down means you add back the continents, you add back the countries, and so on. So in terms of facts table, this is what you would like to have, basically. So I have maybe 8 values that are for every city, and then I have the totals per country. So all of Germany, all of Switzerland, all of India, all of China, for example, here. Then I have my aggregate for Europe and for Asia, and then the whole world. So you see, it's a bit similar to what we've done before with our subtotals for the entire dimensions, except that now the difference is this is only one dimension, but on multiple hierarchical level, continent, country, city. So you see the structure is not exactly the same, the way that the nulls look like, right? So basically, the way you display it is that if you had, oh, the light is really not great. Can I do something with the light? Maybe like this, maybe a bit better. So typically the way that you do things in a visual, if you want to display it on sheets, is that you have here Zurich, Geneva, Interlaken, then you have this L-shaped cell that is a header that says this is all of Switzerland right here. So this is the total for Switzerland. Then you have Berlin and Frankfurt, then Germany as an aggregate of Berlin and Frankfurt, and we have this L that basically shows you the total is here. Then we have Europe, that is Switzerland and Germany, but again, it's L-shaped, so this is here. Then we have India and China that I added, and then the whole world finally there. And this way of displaying the L shapes in the header is one of the easiest ways that people understand what you are doing in a display, right? So accountants really like to see things displayed in this way. And again, this is the same thing. So here, it was only for one specific, maybe just Peter or just Mary, I don't know. But then all of the data that is here basically corresponds to one row over there. And then you have it again for Mary and again for the total. So what is this view? Now, to use terminology I've already been using, this is a cross tabulation, right? I have 2 dimensions. I am dicing on who and on where. Who is on the rows, where is on the columns. All the rest are slicers. And if I don't put them, it means fully rolled up. I just aggregate on every other dimension. And then you see that dicing is compatible with these hierarchies because with the L shapes, I can show an entire hierarchy of the dimension that I put on the columns, right? And then I have all of the data right there. Now, you could ask me, okay, what about L shapes for the rows? This is something people don't typically do. You could, of course, do the L shapes for the rows, but typically, if you want to have totals on the rows, it would be more classical, right? You probably already saw a bank statement and so on. So what you do is you just add some lines, a full line or a double line under total, and you put it in bold, and then you see it's a total. So people are not going to use these L shapes for the row dicer, only for the column dicer. Okay, so I could actually, maybe I should do it. I could have put basically a double line right there and put this in bold to basically emphasize that total is an aggregation on Peter and Mary. The other way that I'm saying people don't really do would to have Peter, Mary, and total here as an L, right? I could also have had an L around Peter and Mary, but it's, again, people don't typically do that on the rows, only on the columns. Okay. Now, how do I compute this, right? If all I have is my original data that I just imported from the rest of the company databases here, how do I pre-compute these subtotals there? Well, back to SQL, this is what it would look like, right? You select the year and the quarter. So now I do it with times instead of countries. You have the year and the quarter, then you have the totals by year, and then you have the all times total. So that's again, this would be the three tables that you would get, right? Now, if I add back my nulls in order to shape them in the same with the same columns, I do the union, right? So you see now I have all of my data per year and quarter, then the aggregates per year, and then the all times aggregate. I can use a grouping sets, right? Year, quarter, year. But you probably realize that that's not a cube here. Do you see the difference with what we've seen before? Here we have year, quarter, then year, then nothing. What did we have before when we were doing it on multiple dimensions? We had year brand, then year, then brand, and then nothing. So this was a cube, right? But here it's not exactly the same thing, because it's not like we have year, quarter, then quarter, and then nothing. We don't have the quarter alone. In fact, it wouldn't make sense to have the quarter alone. What would it mean to have the data on Q1 over all the years? Maybe some people might be interested if they want to see trends in the quarters of the year, right? But typically you don't do that. You aggregate by quarter every year, by year and nothing. So as you imagine, there is a different keyword, then it's not grouped by cube, it's grouped by rollup, right? And the difference is that rollup is basically grouping on this, and this, and this. It's basically, imagine something coming from the right, you just roll up like this, right? So this is what you get. As opposed to cube, cube would be the full Cartesian product, right? Nothing, year alone, quarter alone, and everything, right? So again, to make it maybe even clearer, if I have n attributes here, how many grouping sets do I get with group by rollup? N attributes. How many rows here? So in the case of 2, yes, that's 3. What if there had been 4? What if I had 4 levels here, 4 attributes? Yes? That's sorry? N-1 in the faculty. That could have been, yes, if the order had been important, but here the order actually doesn't matter. So in fact, you're almost there, but it's even simpler. Yes, the sum in the sense that 1 plus 1 plus 1 plus 1, it's just n plus 1, right? You just roll up the whole thing. So for example, let me explain if we have group by rollup A, B, C, D, E. So I have 5, group by rollup A, B, C, D, E. What are my grouping sets? Nothing, A alone, A and B, A, B, C, A, B, C, D, and A, B, C, D, E. So it's n plus 1. Who agrees with that? Right? If I had 6 attributes, I would have gotten 7 rows in there. The plus 1 is just because of the empty one that gets added. But apart from that, you have 1 row that ends with each one of the attributes, so n plus 1. What about the cube? If I do group by cube and I have n attributes, n here, what do I get there? So imagine I had 3 attributes there instead of 2. Year, brand, and customer. How many rows do I get there? On Zoom, maybe? So what I need is basically all of the possible combinations of dimensions. So basically, it's combinatorics, right? Either a dimension is here or it is not there. So there are 2 possibilities for every dimension, 2 times 2 times 2 times 2. So it's 2 to the power of n, right? It's called the power set mathematically. It's basically the cardinality of the power set of the set of attributes, right? So you can do it, again, do it on paper, try to express the same thing here, but with more than 2 cube, and try to write down this list here. If you have n attributes after cube, you're going to have 2 to the power of n grouping sets here. And if you have group by rollup and you have n attributes in there, you're going to have n+1 grouping sets in here. All right, yes, you have a question? Maybe we can with the microphone.
So grouping sets are always 2D slices of a cube?
So the grouping sets are just this union thing, right? This is all it does. It basically does the union of all the possible group bys for every one of the different sets of grouping keys that you have, right? So if I show you on that example right here, you have year quarter that triggers this one. Then you have just year that triggers this one. And then you have nothing that triggers this one. So every one here corresponds to one there, right? This is just a shortcut for the union of group by queries, one grouping by with this, one grouping by with that, and one grouping by with that, right? And then the second shortcut, because there's two shortcuts, is rollup. And rollup is doing this way of quarter and year alone, and nothing. And you see there's n+1 way that you can put my hand in there. If there are n attributes, there are n+1 ways I can hide from the right the attributes, right? So this is group by rollup. And group by cube is that I can either have the both of them, or just the brand, or just the year, or nothing. So rollup means I had from the right. Here, it means that I have plenty of hands, one hand for attribute, and I can either hide or not hide the attributes, right? So this is why 2 to the power of n for cube and n+1 for rollup. You understand? Okay. So the cubes are when you compute the subtotals on multiple dimensions like that. And the rollup, group by rollup, is when you compute in a dimensional hierarchy like that, right? Quarter and year, and everything. Okay. And when you cross-tabulate, this is what you could potentially get like that. Okay. So now I really don't want to scare you, so I put that slide for completeness, but you don't have to worry. Just for you to get an idea, this is what MDX looks like. It has these square brackets around the values, and then it looks like SQL, but with these extra square brackets. And you see you can dice on the columns, you can dice on the rows. This is something you cannot do with SQL, right? But don't worry, I don't want you to learn MDX. I'm just showing to you what it looks like and the sort of things that you can do. You also have a where clause and so on. So you see, you can directly query cubes with that language. And finally, and this is also not material, it's just so that you get a feeling, there is XVRL, which is a syntax for cubes that is used for mandatory reporting all over the world, in the US and so on. It might also become in Europe and in Switzerland a standard as well for climate disclosures. This is all using XML, which is not covered in that lecture. So this is why you don't need to worry. But basically, you see these are like these little cells. You report the little cells of your big cube, like the assets of Coca-Cola on that date in dollars. This is all reported in the XML syntax like that, right? But this is in big data for engineers, this syntax. It has graphs, DAGs, and so on. But again, I'm not scaring you with that. You don't need to worry. This is just so you know that there is a syntax for data cubes, and it's used by regulatory authorities like the governments and the market authorities for reporting data. All right, that's my final slide. This is the architecture of a data warehouse, where again, you take the data from the databases of a company right there, you pour it over in cubes in a data warehouse, and it turns out you can do it on top of a relational database with SQL, but with an extra cube abstraction. We are done with data cubes. This is it. So I encourage you to try it with a spreadsheet software to slice and dice just to get a feeling of it. Go again through the SQL queries and make sure that you understand what's going on. Group by cube, group by rollup, and so on. So thank you very much, everybody. It was very quiet today, but I hope you nevertheless understood everything I've been telling you. Don't hesitate to ask questions offline. Enjoy the exercise session. Thank you, Mark, for moderating, and I'll see you next week for probably the architecture of PostgreSQL and a wrap-up. Thank you very much. Have a good weekend.